Yeah, we can start our class today. I want to look at arithmetic circuits for zero knowledge proofs. I think this is the only topic we needed to cover, and then we begin zero knowledge proofs. So this is to assist us know how to write. So we'll be learning how to write circuits in zero knowledge proofs. So as I've said, the arithmetic circuit will just be a foundational tool for constructing zero knowledge proofs. So for us to write zero knowledge proofs, then we need to know how to write the arithmetic circuits. Arithmetic circuits is not, these are just equations, and we'll be having signs like addition and multiplication, and then equality. So these equations will then be assisting us to do computations and verify computations of zero knowledge proofs. It's not the only way to verify computations. That I'm saying that the arithmetic circuit is not the only way. We also have what we call the Boolean circuits that are used in verification of zero knowledge computations. But the arithmetic circuits have an advantage over the Boolean circuits. I've said, for instance, although the Boolean circuits would require the logic gates, which would then use and, or not. You understand the logic gates. And what happens this time is that if you're using the Boolean circuits, the inputs must first of all be converted to binary. And so that then means that we'll be dealing with a very big input. Even if it were a very small input, you must convert it to binary. And now the arithmetic circuits goes around that so that we are not converting anything to binary. So I've said, unlike the Boolean circuits which rely on logic gates and require multiple variables, now the multiple variables are coming in for the reason that every entry has to be converted to binary. So then it becomes multiple. Because you'll be entering all those digits. But the arithmetic circuits will be using addition and multiplication directly without necessarily having to convert entries to binary. So that is that. But they'll be doing the same thing. The Boolean circuits and the arithmetic circuit will be doing the same thing, only that the arithmetic circuit have advantage that I've mentioned over the Boolean circuit. Now, we had already talked about finite fields. We've looked a lot about finite fields and the rings, and we are saying that these circuits are on a finite field. And our inputs will be expressed as polynomials. We also look at polynomials. And this is an advantage that I already mentioned, that we will not be talking about Boolean expressions this time. That will be wanting us to convert everything to binary. We'll just be dealing with the polynomials this time around. And we had already looked at how to do operations with the polynomials, so we are very comfortable with that. Now, so just before we proceed, what we'll be doing when we talk about arithmetic circuits, we're just referring to equations. And these equations would have addition and multiplication as the signs, and then there'll be equality. And they'll be assisting us to do to verify computations. Remember that when we go to zero knowledge proofs, we have the verifier and we have the prover. And so we'll be seeing how to write equations that can perform those tasks where we can verify computations and prove those computations. That's what we'll be doing. And I've said here that many zero knowledge proving systems, such as snarks and stacks and the bulletproof, would then rely on these arithmetic circuits, define computations efficiently in a form that is suitable for cryptographic proofs. So that then means that it's not very easy to write zero knowledge proofs if you don't understand the concept of arithmetic circuits. How do you write equations that would then be used to verify? Now, there's something we shall also look at after we've looked at the arithmetic circuits. We shall be looking at rank 1 constraint. That will be the next topic. And once you've done the arithmetic circuits and you've done the rank 1 constraint, you are now comfortable to write zero knowledge proofs and verify computations in zero knowledge proofs. But what I've noted here is that though we've not reached the rank 1 constraint, I've just noted that the arithmetic circuits would naturally translate into rank 1 constraints. If you read books, rank 1 constraint system would be abbreviated by R1CS. This is just a standard representation in zero knowledge proofs that allow efficient proof generation. Because you'll be generating proofs and then at the same time verification of the proofs. So rank 1 constraint system allows us to do that. And so it's very important to understand then the arithmetic systems, the arithmetic circuit, because we will see later when we'll be looking at rank 1 constraint that the arithmetic circuits just translates into the rank 1 systems. So it's important how we then be writing those circuits. It's very important how we be writing them going forward. So I've already mentioned this last point, just for emphasis, that by constructing computations algebraically, arithmetic circuits would enable efficient construction of proofs, where the prover can demonstrate knowledge of a valid computation without necessarily having to reveal the underlying inputs. So that is what the prover does in the zero knowledge proofs. So we have the verifier, we have the prover. So the verifier wants to know whether the prover understands, has knowledge of what he claims to have. So the prover would then use these arithmetic circuits, to prove, just to demonstrate that he has the knowledge or she has the knowledge of what he claims or she claims to have. Using the same arithmetic circuits, the verifier will be able to verify that the knowledge, the information given by the prover is correct without necessarily having to know what the information is, what the inputs were. So we'll be looking at that. There's a small example here. And this example is just a comparison. As I stated, I said that the circuits we're talking about can be done by Boolean or arithmetic. So this is just comparison. I've already said that the arithmetic circuits have an advantage over the Boolean circuits. Though they be doing the same thing, we've not looked at the Boolean circuits. If you have time, you can look at the Boolean circuits. But I'm just saying, if you are to look at it, you would then discover that the arithmetic circuits will have an advantage because one of the difference and the advantage comes from there is that the Boolean circuits would represent computations using binary variables and logic gates. So what I said is you are given a computation under Boolean circuits. At this computation, the inputs would then be converted to binary variables, first of all. But the arithmetic circuit is not doing that. The arithmetic circuit, we have, instead of the logic gates, we have plus and multiplication direct in our equation. So I've said, however, that is, again, just to talk about the Boolean, I'm saying, however, even a simple arithmetic operation requires complex Boolean encodings, leading to large and intricate circuits. When you are dealing with the Boolean circuits, even a small the operation for that, if you're doing a computation, you want to verify, you have to convert to binary, and so that would make the process works. For example, if it was to just A plus B, and it's very bad weather, so it really interferes with the network. Now, so I was just giving the differences between Boolean and the arithmetic circuit, and of course, what makes the arithmetic circuit better over the Boolean. So I was saying that if you are to have a very simple computation like the one we have here, and I was just telling you that, you see, these circuits will not be generating this proof, will not be generating this equation. What they're doing is just to verify that A plus B would then give us C. Now, under the Boolean circuit, first of all, you would then convert A to binary, convert B to binary, convert C to binary. And then you would then want to, from there, that is when, after conversion, that is when you might maybe want to do the summation on the left and see whether it equals to whatever is on the right side. That is under Boolean algebra. But The arithmetic circuit, you just do it the way it is. You just add a plus b directly because we have the plus sign and then we have the equal sign, and you can see whether whatever equals to whatever is on the right side. So that means therefore the arithmetic circuits are easy to deal with, and that is what I've said here. That in contrast, an arithmetic circuit expresses computations using addition, multiplication, and equality constraints, directly modeling the problem in a structured algebraic form. Therefore, and again, just to emphasize, arithmetic circuits verify correctness. They verify correctness without necessarily computing the intermediate binary representation. So we don't require to get the binary representation of A. We don't require to get the binary representation of B, and so on in the arithmetic circuit. But that would have been the case under the Boolean circuit. Now, so what is an arithmetic circuit, therefore, formally defined? What is the formal definition and an example? So I want to give a definition, and I'm saying that an arithmetic circuit, therefore, is just a system of equations. And this system of equations would involve addition, multiplication, and equality. It's just a system of equations that have addition, have multiplication, and have equality. This is an example of that system of equation. You can see this system has addition, has a multiplication, and then has equality, the equal sign. Now, what does the arithmetic circuits do? They do not generate these equations. They just verify whether the inputs are correct. The inputs, you just want to verify. You see, the prover would want to verify that he knows what x1 is, what x2 is. So then the verifier will be giving you, but without necessarily telling you the exact value of x1 and x2. We'll be trying to show you that he knows what x1 is or what x2 is. So I've said it verifies whether a given set of inputs satisfy the defined equations, but does not compute a solution. Does not compute a solution. It just verifies that the inputs are correct. Now, so for instance, considering the equations here, this is an example of an arithmetic circuit. So what could be the values of x1 and x2 that will satisfy this equation? Now, I've said that the values could be x1 could be 3 and x2 could be 3, and we just test and see whether the values are proposed to satisfy this equation. Like the first one, 6, it's true that 6 will be equal to 3 plus 3. And at the same time, now equal to 3 times 3. So that means if somebody was to tell you that x1 was 4 and x2 was 2, you just come and verify. It's true that 6 will be equal to 2 plus 4 or 4 plus 2, but it's not true that 9 will be equal to 4 times 2. It's not true. That means this person would then be lying, because whatever value of x1 that is given or whatever value of x2 that is given is supposed to satisfy these two equations. Supposed to satisfy these two. So this is just an example of an arithmetic circuit, and that's why we want to be learning how to write this arithmetic circuit for zero knowledge proofs. So what has it done? It has just verified that the inputs given to you are correct. In this case, it has verified that x1 is 3 and x2 is 3, and any other values will not be correct. But the thing is, the inputs must satisfy the system of equations. The system of equations is just all the equations given for that purpose. So there could be 2 equations, there could be 3 equations, there could be 4, and so on. But now the solutions or the inputs must satisfy all those equations. Now, so just before we learn how to write this arithmetic circuit, so we need to know some notations and some constraints. Some notations and some constraints. Now, in the previous equation, when we're writing in Rust like this, then instead of this equal sign, we'll be using this. Be using that. Okay, just before that, I've said that in arithmetic circuits, the variables x1, x2 that we've seen above would then be referred to as signals. The variables will be referred to as signals, and the equality relation will be denoted by this and not this. Now, so that if I write C equals to A plus B, this is what I'll be using. C equals, so this is the equality sign. And is equivalent to writing, is equivalent, if you don't want to write it this way, if you don't want to write it this way, then you write that assert equation, C, then comma, A plus B. No, assert equality here. That's equality. Now, so C, and then we know that because we are talking about the equality, then it will be equal to A plus B. So instead of writing this, you may also want to write it this way. Similarly, if I wanted to write that the sum of A and B equals to a product of C and D, I can write it this way, or you may also want it to write it this way. Whatever is on the left side is here, and whatever is on the right side is here. The product. The same thing here, whatever was on the left side was on the left, and whatever was on the right side was on the right. So that is the other way of, that's how you can write, and these are just notations. So that as when you begin writing this, when you begin writing the arithmetic circuits, and then we know what we are writing, we know the symbols we are using, even as we do it in Rust. Now, again, I said the essence of the arithmetic circuits is not to come up with equations, just to verify. So I'm saying verifying equations in an arithmetic circuit ensures that all the constraints hold for a given set of inputs. Constraints, we've been using the word constraints. These are the equations. These are these equations that we're coming up with. One, to ensure that whenever you put the inputs, those equations hold. Those constraints hold. So a prover can assign arbitrary values to the circuit signals. Remember what I said circuit signal is? I said these are the variables. But the proof is valid only if this satisfy all the constraints. Remember, an arithmetic circuit is not just one equation, there are several equations. That's why I call them a system of equations. So you have the liberty to assign a value to the to those signals, or to those variables. But as you so I was I was um, I was saying that this is the equality that we talked about. So again, just to emphasize this, because we'll be writing this in Rust, then we need to know how we'll be writing the equality. Now, supposing the prover wants to demonstrate that it knows what A, for instance, is, what B is, what U is, what C is, and we have this are as the constraints. If these are the constraints, then that means the prover is supposed to provide A, B, C, U, X, and Y. And all this. And then they must satisfy all these equations. Now I said that instead of writing this in Rust, you may also want to write it this way, and it means the same thing. You can see this is the same thing we wrote. The one on the left is here, assert question, and whatever's on the right is here. Same thing to this other equation. So when we come to that, we'll again know, we have to recall that is how we can write it. So what you're saying is the prover, for him to demonstrate he knows these values, he's supposed to provide A, B, C, U, X, and Y. And those values must satisfy the two equations given here, not just one equation. We want to look at an example of an arithmetic circuit. Now, to illustrate the concept that all signals in arithmetic circuit are inputs, and that this operator is used to check equality rather than assign. So this example is just to verify that. We say that this is just to, this operator here, equality sign, is used to just to check equality, but it's not used to assign values. Now we consider this example, So this circuit has two constraints. So I'm still using those terminologies so that we get used to them. Two constraints. This is a circuit, this is an arithmetic circuit with the two constraints. The term that is used and the term that we'll be using is constraints. Now, we shall be talking about witnesses when you talk of zero knowledge proof. A witness Witness are just the values of the signals. Is what we call the witness. Is a witness, and the person verify, the person proving it can also be called a witness. But now, for our case, a witness would be the value of x, the value of y, the value of z, the value of u. So the prover must provide this witness, these witnesses. And so the x that is input here and the y, z, and so on must satisfy this equation, and at the same time satisfy this other equation, not just satisfying one equation and stop there. So the witness, let's take a witness. Okay, so we have the terminologies. We have the prover, the person claiming to know the witness. The person that claims to know some knowledge, to have knowledge of something. And we have the verifier, is a person that wants to verify whether the prover knows or has the knowledge of the thing he claims he has. And then you have the witness. The witness are the values the prover will be providing. These values that the prover is providing are not necessarily what he knows. The answer that he knows could be 2, but he now be providing maybe 3. Just to show, but once he provides that 3, you verify that the 3 that is provided and maybe the 4 that is provided fulfills the x here, and also whatever is provided here fulfills this. So he may give you 3, may give you 4, but he knows the exact answer, maybe it's 2 and 5. So for you, just to verify, once you know that you are sure that what he has given holds, the equation holds, then it means he knows the answer also. It means he knows the exact answer. Now, so these are our constraints. Now, let's see the type of witnesses the prover could give that would fulfill these equations. The first one, we want an x that is given, if placed here, and a y that is given, if placed here, these two should sum to 4. And that x that is given and the y that is given, and there's a y, z also given, these two must sum to x. So let us see the kind of witnesses this prover could give. And we will see which one is correct. And you see, let me again emphasize, when the prover gives x, y, and z, this is not what he claims to know x. He claims to know x, he claims to know y, he claims to know z. So when he's giving some values for x and y and z, those are not the exact values. The exact values will be held. That is a secret. But he's just giving you other values to prove he knows what x is. Now look at the first witness. The first witness, he may give us x to be 4, may give us y to be 1, z to be 3, and then u to be 5. So it's now the work of the verifier to check whether the witness given satisfies all the constraints. So the prover would now place the equation, the constraint was x is equivalent to z plus y. And then the other constraint was 4 would be equal to x plus y. So the prover the prover says he knows where X, Y, and Z, Z and U are. Then you ask him to show. Then he gives you this. He gives you X to be 4. So you just try and put 4 here. Put where there is X, you put 4. And then he has given you Y to be 1. So put 1 where there is Y. Then he has given you Z as 3. So you can see by that, the first constraint has been satisfied. It's true that 4 equals to 3 plus 1. Now you check the second constraint if the same values would fulfill. The second constraint had 4 equals to X plus Y. So just put X here. X is 4. Then put Y. Oh, I think I typed wrongly here. This one was supposed to be 5. This was supposed to be 5. This is supposed to be 5. So 5 equals to put X here as 4 and put Y as 1. So you can see it's true actually that 5 equals to 4 plus 1. So that witness is correct. That witness is correct. So you may again want to ask him to provide other values. You want him to provide another witness. But the first witness has satisfied both constraints. So then he provides another witness again. He provides another witness, and it is upon you now as the verifier to check whether the witness is correct. So the witness, let's again, I again recall the constraints. Let's again recall the constraints. Okay, the constraint was X constraint was X is equal to Z plus Y. And remember our equality is this, I'm just writing, but you know, and 5 is 1. Now we okay, so the first constraint is this X. So where there is X, you put the value of X is 7. And where there is Z, you put the value of Z, which is 5. And where there is Y, you put the value of Y, which is 2. And this is satisfied. And this other constraint, this is supposed to be 5. The constraint is supposed to be 5. 5 equals to x. X is 7 and y is 2. So that means this constraint is not satisfied. I think I typed 9, so I was seeing, but it's not satisfied. This one is not satisfied because the constraint from our question is supposed to be 5 equals to x plus y. But 5 is not equal to x plus 1. So that means the witness given is not correct. But for the first example, the witness was correct. Let's look at this other example. Again, I can say I did a mistake because this was supposed to be 5. This was supposed to be 5. But now, the other one was x is equals to what? X was, is it? I don't know what I remember. Was it x is z plus y? Yes, x is z plus y. This is supposed to be 5 here. 5 is that. I can make it, can correct it. Because I can say how are you here. I can say how are you. So in fact, the mistake is here. The mistake is here. This is supposed to be you, not 5. It's supposed to be you, not 4. So it's supposed to be you. So that if it's you, let's again go through the constraint. If it's you, because I can see I had a u and I'm not using it. So if it is a u, then what happens? X is equals to z plus y, and u is equals to x plus y. Let's see whether this witness satisfies that. So x is 4, then z is 3, and y is 1. So this is correct. Now let's check whether u equals to x plus y. U is 5. U is 5. X is 4. And y is 1. So that's correct. That's correct. This witness is correct. Now let's check the second witness. That one is supposed to be you, not 4. Because of typing, I think I typed the wrong thing. Okay, so the same constraint, we use it now on this. Use it on this second witness and see whether the second witness is correct. So this is the witness. X is 7. Then Z is 5. Then Y is 2. So this is correct. Then what about U? U is 9. Yeah, this is now correct. U is 9. Then X is 7. And then Y is 2. And again, this witness is correct. This witness is correct. Now, so what we are doing is we are given constraints, and the prover wants to prove that he knows what X and Y and Z and U are. So it's upon this prover to provide those values, and he's not providing the exact values, just providing any other value so long as they satisfy the equation. But it's not just so long as, because as we go further, you'll see that, and again, the prover has to ensure that those values are within the limits. So we'll see how we now impose the limits, because he may give you values that are outside, but they will still satisfy the same equation. Because when you are dealing with, for instance, you are dealing with finite fields, mod something. you want to find out that the prover, though it's giving you values, these values are supposed to be within this range. So that it's not giving you values outside that range. So that's the next thing we'll be looking at. But let's look at this other witness just before that. Want to see whether this other witness is correct. So the prover has given us another witness, claimed to know X, Y, and Z and U, but now has given us this. Now, our constraint is still the same equation here, that X will be equal to Z plus Y, and mu will be equal to X plus Y. So you just prove, you just insert X insert Z and insert Y. And see whether they're correct. And see that the equation is not satisfied. On the right side, we are seeing 8, and on the left side, we are seeing 4. About this other one, U is 7, X is 4, and Y is not been satisfied. All the constraint circuits, so it's the verifier. Yeah, I was saying it's the verifier who asks the prover, not the other way around. The verifier asks the prover to provide, to show that he knows, to prove that he knows X, Y, and Z. So the prover then gives the witness. And so at the verification stage, you're now checking whether the witness given is correct. Now, again, our example above, we've just shown that when you be writing Rust, this operator will be used for equality. That's what we'll be using. And of course, we've seen the other way of writing same equations using the assert equal. Now, I'm saying that the circuit could also be written like this. There's no problem. You see, the initial one, we had written it like this. We had written that X is equal to Z plus Y, and that mu was equal to X plus Y. So you can just interchange. You can even begin with this and then that. There's no problem. So when you're writing Rust, there'll be no problem. You can begin with any. Let's look at this circuit. Let's look at this circuit. And this circuit, I just want to emphasize this equality. So what is the role of the equality sign? This one. You see, in normal Rust, whenever you write X equals to X plus 1, what it means, or what is it, how it's interpreted, is that X has been incremented. So X has become X plus 1. So if X was 4, the new X becomes 5. That is what normal Rust would then interpret this. That is how Rust would interpret this. But that is not the same way it interprets this. That is not the same way it interprets this. This way, this one, it will be interpreting that x is incremented. And it's increased by 1. It's increased by 1. But this is not the case for, it will not interpret this one. That's why we are not using this. We'll be using this one to write our zero knowledge proofs. And we know what it means. What it means here is that the prover is supposed to give us an x. Supposed to give us an x, which when you input here and input it here, this equation should hold. This equation should hold. So that is how it would be interpreted. And you can see for this case, it's not possible to have an x. To have an x that will satisfy this equation. It's not possible to have an x that will satisfy this equation. But you have an x, you put it here and you put it here, and it gives you whatever is on the right equals to whatever is on the left. It's not possible to find such an x. But the point is, while writing our knowledge with no quantity and interpreted differently by the program. Program will interpret. So this now, so again, just to emphasize on this example, now we know what it means. We know what it means. It means that there is a witness x, which when you put on the left side and you put on the right side, this equation will hold. But you can see in reality, this x does not exist. We can never get such an x. And therefore it means that this constraint has no valid witness. It has no valid witness. We can never get an x that would satisfy this equation. Now let's look at these other constraints or arithmetic. These are arithmetic circuit. Let's look at this arithmetic circuit and see. Of course, we know how programming language will be interpreting this. We shall also be interpreting it. These are two constraints. These are two constraints here. So the prover is supposed to provide witness x1 and provide witness x2. What are the possible values of x1 the prover can provide here? Using the first equation, when you look at the first equation here, the possible values of x1 could be 0, and x1 could also be 1 when you equate this to 0. Those are the possible values of x1. So x1 is supposed to be 0 or 1. But then the prover is also supposed to give us x2, because whatever is given is supposed to satisfy these two equations. So, but the prover is also keen. He also knows, while giving the values of x1, he knows that if he was to give any other value other than 0 and 1, then the first equation would not be satisfied. The first equation will not be satisfied if he was to give any other value, because x1 to be 2, then 2 minus 1, there's no way it can equal to 0. There's no way it can equal to 0. So the only values of x1 that is likely to give are those. But now, which one specifically? Because now he has to come again here and find out what x2 would be. So supposing x1 is 0, what are the possible values of x2? Supposing x1 is 0. So if x1 is 0, then x2 can be anything. If x1 is 0, x2 can be anything. x2 can be 0, can be 1, can be 2, can be 3, can be 4, can be 5, and so on. Because it means 0 times anything will just be 0, because we've said x1 times x2 is x1. So if x1 is 0, this prover can give you any of these values as x2. What about if x1 is 1? If x1 is 1, what can x2 be? So you're looking at a value that when multiplied by 1 gives you 1. That value is likely to be 1 only. It's likely to be 1. So that means if the prover gives you x1 to be 0, then he can give you x2 to be any value, even 5. But if he gives you x1 to be 1, then he's likely to give you x2 to be 1, but not any other value. So just trying to understand this constraint and what the prover is likely to give us if we were verifiers. So what we will then be learning is how do we come up with such circuits, because this is a circuit. So depending on the situation at hand, how do you come up with this circuit that will then be using to verify? So this is just explanation of what I've already explained. I've said if x1 is 1, then x2 must also be 1. Otherwise, if x2 is not 1, then the second constraint will not be satisfied. So what about if x2 is 1? No, x1 is 1 and x2 is not 1. If x1 is 1 and x2 is not 1. So supposing the prover is giving us something different for x2, that will not happen. X2 cannot be any other value. So the equation will not be satisfied. Now, if x1 is 0, we've already said that x2 can be any value at that point. So part of the witnesses we expect from the prover would be 0, 0, where x2 is x2 is 0, x1 is 0, or can give us this, or can give us this, or this, or then this. This is when x1 is 1. So those are the kind of witnesses we expect. Now, this is just the differences between Boolean circuits and arithmetic circuit. From the start, I began by telling you the difference. And I began by telling you that the two would perform the same thing, only that the arithmetic circuits have an advantage over the Boolean circuits. But now these are the differences. You can look at them later. This example has already been explained. I already explained that Boolean circuit has a disadvantage such that even for simple computations like A plus B is C, the Boolean circuit would require that you convert A to binary, convert B to binary, convert C to binary, and then after that, you verify the computation. Now, this would to very large inputs. Very large input. Like for the arithmetic circuit, I would just do the computation directly. If you have A plus B, the arithmetic circuit will just do A plus B and then verify that it equals C. So I'm just an example that the Boolean circuit has a disadvantage. Suppose this A is a 4 after converting to I was explaining the disadvantage of this Boolean circuit. And I was saying, supposing A is 4 and B is 5 and C is 9, and you want to verify that whatever is on the left equals that. Okay, you'll be using logic gates. You're not using plus, you'll be using logic gates. But now, the thing is, this 4 will be converted to a binary. Let me say, for instance, you get this. We just say you get this. This is a 4-bit. 1, 2, 3, 4. And let me say that this one, maybe you get 0, 1, 0, 0. Just an example. And let me say that this one, for example, you get 1, 1, 1, 0. So each of these are 4 bits. So these are 12 inputs. If you are using the Boolean circuit, you'll be having 12 inputs. But for the arithmetic circuit, you just have 3. Just have 3 inputs. This witness, and this witness. So that makes the computation very easy, straightforward. So this again is just an emphasis of the advantage of arithmetic circuit that we'll be looking at. Whether we learn how to write the arithmetic circuits for zero knowledge groups. Of course, I said they'll be doing the same thing, only that one has an advantage over the other. Now, so I think we can stop at that, so that when we meet next, we look at the three coloring problem with the arithmetic circuit. And this will be a way of getting to know how to write the arithmetic circuit. For instance, if you want to color and so on, you have three coloring problem is where you have, for instance, you have a map, and you want to ensure that in this map, any two adjacent locations are colored different using different colors, so that we don't have adjacent points colored with the same color. Now we'll be seeing how to write constraints to assist us do that coloring. Writing equations. Equation will be assisting us to ensure that if I wanted to color the map of Africa, Kenya is neighboring Tanzania, they should have different colors. And I have only three colors. This is a three coloring problem. I have three colors, and I ensure that Kenya is bordering Tanzania, is bordering Sudan. Each of these, we have no countries that are neighboring each other that would be mapped, would be colored by the same color. So we'll be seeing how to write equations to do that. So I want us to stop there. Just today, just wanted us to know what an arithmetic circuit is, and some of the terminologies that we'll be using while writing the circuits going forward.